So this is the final leg in our approach of summarizing Chapter 3 and trying to explain the monetary approach to exchange rates in the long run. And in Part 3, what we're going to do is to add a brand new variable of interest rates now into the model. And this will give us our final monetary model that explains exchange rates in the long run. We have one final variable that we have to talk about in order to finish up the monetary approach to explaining exchange rates, and that is we've got to add interest rates in, because it turns out that money demand is highly influenced by the interest rate. So ignoring the interest rate could have pretty big implications on our model. So what we're going to do is we're just going to take the existing model that we have and add in interest rates into the real money demand equation. So in place of L just being a constant that never changes, we're now going to argue that L does change according to how the interest rate changes. So we'll say that L is a function of the interest rates, and how it gets impacted will impact real money demand. And this kind of makes sense, because if you think about it, if interest rates were extremely high, you would probably be a little less likely to pull money out of savings or out of your deposits in order to engage in transactions and buying goods and services in the economy, correct? I mean, after all, think about it, you'd be losing a lot of money if the bank was willing to pay you a lot of money to keep your money in the bank account. So you might want to think about that. It does impact transactions, and so it does impact the money demand. So we're going to add in the interest rates, and we're going to argue that money demand is a function of interest rates and real income. So this is a much more realistic model of money demand, and we are going to now set this money demand equal to the real money supply. But now, of course, interest rates are now a function of real money demand. Now, let's recall these two equations. We talked about them before. We talked about UIP in Chapter 2, and we've talked about relative purchasing power parity earlier in this chapter. Now, relative purchasing power parity told us that the expected inflation differential should give us the expected rate of dollar depreciation, or the change in the expected exchange rate. And then we also learned back in Chapter 2 that uncovered interest parity, that we had an approximation for that equation, and the approximation was the net dollar interest rate minus the net euro interest rate, and that would equal the expected rate of dollar depreciation. So this lets us set the nominal interest rate differential equal to the nominal inflation rate differential. After all, the left-hand side of the equation were the same, so clearly we can set these two equations equal. If the change in the expected interest rates are the same on both sides, on both of these equations, clearly we can set the expected inflation differential equal to the net dollar interest rate minus the net euro interest rate. Now we're just going to rearrange these terms, and we're simply going to have the United States values on one side and the euro values on the other side. So if we take the interest rate and subtract off the rate of inflation, expected rate of inflation, and we can set that now equal to the interest rate in the euro minus the expected inflation rate in Europe. So subtracting the inflation rate pi from the nominal interest rate I results in the real interest rate R by definition, and that's what we refer to as the Fisher effect. In fact, this equation represents the Fisher effect, because the Fisher effect tells us that the real interest rate is equal to the nominal interest rate minus the inflation rate. That's known as the Fisher effect. And that's what we get here on both sides of the equation. Nominal interest rate minus the inflation rate. That's what's known as the real interest rate, and is the Fisher equation. So now what do we have? Well, we have that the real interest rate should be the same in both countries. It tells us that, and this is an important result that follows from the PPP and UIP, assuming, of course, they both hold, that we expect now that the real interest rates in both countries should equalize. That is, we call this the real interest rate parity, and we expect that interest rates normalize and are equal across all nations. Now, of course, this requires capital accounts to be open, obviously, and which allows arbitrage to take place. So arbitrage in goods and financial markets alone is sufficient in the long run to cause equalization of real interest rates across countries. And this is what we would expect. This is kind of a powerful statement because what it's really telling us is that the real world interest rate is outside the control of policymakers. That is, policymakers can't impact the real worldwide interest rate, because if capital accounts are open and arbitrage takes place and purchasing power parity is true, then we would expect that over time that all interest rates would normalize and equalize, and we would have a real interest rate that would eventually become the world real interest rate. And we treat R star, which is the real world interest rate, as an exogenous variable, again, outside the control of policymakers. And so what this ultimately tells us that is that the interest rate in the United States is equal to the interest rate, the expected one, plus the inflation rate, according to the Fisher equation, which is equal to the world interest rate plus the inflation rate in the U.S. And this is also true in Europe, that the interest rate in Europe is equal to the world interest rate, an exogenous variable outside the country's control, plus the European inflation rate. So as an example, if the real world interest rate, R star, is equal to 2%, and the country's long-run expected inflation rate goes up by 2 percentage points, say from 3 to 5, then we would expect that the long-run nominal interest rate also goes up by 2 percentage points, from the old level of 5% to the new level of 7%. So this is our final model, and notice it's in the form of an equation, but it tells us everything now that we need to know about the exchange rate. And it's told, the story is completely told in the form of an equation. It's a function of the money supply in the two nations, and it's also a function of money demand. But notice money demand is a function of interest rates, so interest rates also play a role here. And what this tells us is that because L varies according to the nominal interest rate I, when interest rates change, the general model has different implications than the simpler model without the interest rate. So now let's consider the same forecasting problem we considered before. Let's raise the rate of money growth from mu to mu plus delta mu. But before we do, I forgot to mention one important impact that interest rates have on money demand. And I said it, but I didn't say the law clear enough. And that is that when interest rates go up, that tends to mean that money demand itself, especially for transactions, tends to go down, because as interest rates go up, you tend to want to leave your money in the bank to receive the added income from the interest rates. So as interest rates go up, your transactions tend to go down because you want to keep your money in the bank. And so money demand tends to go down. And on the other hand, when interest rates fall, you tend to take your money out of the bank more and engage in transactions. And so we tend to see an inverse relationship between interest rates and money demand. So when interest rates go up, money demand in general go down. And when interest rates go down, money demand in general goes up. So that'll be important when we look in the graphs in the next on the next slide. So again, we're going to consider the forecasting problem. We're going to allow the we're going to allow the rate of money supply growth to change from mu to mu plus delta mu. And we'll assume that this is taking place in the United States. And once again, we want to consider what's going to happen in each one of these variables. We'll start with the change in the money supply. So we're assuming that before time t, we have a specific money growth rate of mu. And so looking in the far right top hand corner, the A graph, money supply M, we can see that the money growth rate is mu up until point time t, and then we expect that the slope of the money supply should change because its growth rate is changing, and of course the rate of change of any graph causes the slope to change. And in this case, because it's increasing, we would get an increase in the slope, or a steeper slope. So M, representing the green line here, represents the rate of represents the money supply, and we can see that the rate of growth at time t of the money supply suddenly increases, again represented by the steeper graph at time t. So what's the impact on money balances? Let's look at B, the graph now here in B. So we have two variables here being represented, both the interest rate and the real money growth, the real money balances. Real money balances M over P. This is a level, not a growth. So we're expecting that up until time t, that real money balances are constant, as too is the interest rate. But now, because the money growth has increased and the rate of growth in inflation has increased, we expect that the interest rate will also increase. Now, we know that the interest rate must increase because inflation's increased. By definition, that's what we mean by the growth of the money supply, the rate of growth of the money supply increasing. Because inflation's increased, we also know the interest rate increases. And how do we know this? Again, for that, we go back to the Fisher effect. The Fisher effect tells us that the real interest rate is equal to the nominal interest rate I minus inflation. But again, we can rearrange those variables, and this also tells us that the nominal interest rate I is equal to the real interest rate minus inflation. That tells us that if inflation changes, so does the nominal interest rate by the same amount. So we expect from the Fisher equation that the nominal interest rate I will change by as much as inflation. So when inflation changes, we expect the interest rate to go up proportionately. And the same with money balances. Because the interest rate is going up, we expect money demand to go down. And if money demand goes down, because money demand is equal to the real money supply, we expect the money supply to drop. So we expect a change in M over P to be just as much as the increase in the money supply. So again, the real money supply, or M over P, should change by exactly the same amount as the rate of growth of the money supply increases. Well, this is interesting because if M over P has fallen, and we know that the rate of growth of money supply is increasing, well, that means that M is increasing, so obviously P must change as well. Notice what happens to P. The price level actually jumps and the rate of inflation increases. So not only do we have to get a jump in the price level itself as a result of the increase in the money supply, we're also going to have to account for the rate of inflation increasing as well. So in panel C, we notice that when we plot the price level, we have to account for both the change in P as a result of the sudden drop in money balances. And again, because capital M has been increasing, it has to be that P has to be increasing proportionately to compensate. That is, to compensate for the increase in the money supply. So the price level has to increase significantly. It has to jump to compensate for that increase in the money supply. So the price level jumps, you get a jump in that, but you also get an increase in inflation. Remember, inflation is nothing more than price level changing, increasing constantly. So the growth rate at time t, we see a jump in the price level, and we also see an increase in its rate of growth, which is represented by a steeper slope. So finally, what's the impact on the exchange rate? Well, again, we go back to this equation to describe that. So again, what we've done is we've increased capital M in the U.S. And because we've increased capital M in the U.S., we know that all these other changes have to result in an increase in the exchange rate. So finally, we have to represent that on the graph, and we represent that on the graph in panel D, showing that the exchange rate jumps and the rate of depreciation increases. And so we see the rate of depreciation increasing here by this changing slope, and we see that the exchange rate jumps as a result of this continual increase in the money supply. Well, that's really the long and the short of it. I tried to do this as fast as possible to get straight to the points, to try to summarize and make sure that the storyline that's being told of how we're developing these models, to make sure that I cover all the major points in this chapter. I hope you found this helpful. Let me know if you do. This is a new approach of mine. I've never done this before. But I thought that a cleaner or more precise and to the point discussion on Chapter 3 might be a little bit more helpful for you folks. So let me know if it's at all helpful. I hope it is. And remember that if you want to discuss anything, either on the phone or in my conference website, I'm available most times during the day. Just give me a holler. Talk to you later. Bye.